Oh, hello everyone. I thought I'll make a video which will walk you through some of the problems that we worked out in class on week 3, which includes quiz on mass balance and some problems on energy balance. Okay, so let's start off with the quiz. The quiz is a classic tank draining problem which was given, and many of you got it right. And but the problem was, when I looked at some of what the TA showed me, many of you didn't, and the thought process for some did not look right. So always start off with the definition of the mass balance, which is the net rate at which mass leaves plus accumulation is zero, right? So, and all you have to do now is to work out the different terms. That is it. So obviously for this problem, mass doesn't come in, mass always leaves, right? So a lot of you wrote V in, which makes absolutely no sense. So the net rate at which mass leaves, the rate at which mass leaves, density times area of the pipe times velocity, which is a constant, plus accumulation of mass, which is d by dt of density times area of the tank times h is equal to 0. So the net rate at which mass leaves plus accumulation of mass equal to 0. So that should be a starting point. And you should evaluate what each term is. That is it. So there's just one way to solve the problem. So just be patient, write down the mass balance and work out individual terms, right? So and again, that'll simplify to the simple differential equation for h, right? dh over dt minus ap over at times v. That was part A, which carries 10 points. So you have to show clearly how the height of water or liquid inside the tank is changing with time, and that is what is asked. So again, the common mistake a lot of people did is not writing the mass balance and evaluating it term by term. Of course, you can solve it in a bunch of, you can use different terminology, solve it, but you clearly need to show how the height inside the tank is changing with time, and the differential equation that describes the change of height with time. So going on to part B is just basically solving for T final, and all you have to do is integrate. And I think one key thing in part B is you have to clearly define the conditions, and what I mean by that is at t equal to 0, height h is h, and at another final time of 1 hour, the height goes to 0, or the tank completely drains of the liquid. So it is very important that you clearly state what are known as the not the initial conditions. There's an initial condition and a final condition, right? You clearly need to state your conditions. Or even if you clearly indicate that on the integral, that is also fine. And it's just a simple integration. And finally, when you plug in the numbers, you get a value of 0.25 meters. And again, another thing that I would like to illustrate here is that the advantage of just working in terms of variables and then plugging in numbers at the last minute. And as you can see, for this problem, you do not even need a calculator, and you get a value of 0.25 meters. So here is a piece of advice, people. So please, whenever given a problem, read the problem, draw the schematic, and the schematic was given to you in this particular case. Clearly define your variables, write down the units, and then you're going to work out problems on mass and energy balance. Clearly state the mass balance, clearly state the energy balance, then look at the energy balance and try to evaluate it term by term. And then the problem will really simplify, and you just have to calculate the unknown quantity. So just be patient, follow the steps, and do not jump steps. Think through how to evaluate each term of the mass and energy balance. So we did the quiz, and after the quiz, I think we went on to energy balance, and we worked out some problems, right? So please go through chapter 6, go through the derivation of the energy balance, which you should also be comfortable deriving on your own, closed book. Go through the notes from another book which have been posted online. There are a bunch of problems posted from the other book as well, which you can work out. Work out problems from the book, work out problems from Sham series. The more problems you work out, the more you try to understand the concept, the better you will get. One big mistake everyone makes is they look at the problem, they look at the solution, and they think they know how to solve the problem, right? So please do not do that. Do not give up until you can solve the problem yourself, right? That's very important. Okay, so let's go through some of the problems that we did in class. Shown here is what is known as a flow measurement device. Sometimes people call it this Venturi meter. So what's happening is liquid flows from A to B in a horizontal pipe shown at a rate of 3 foot cube per second. So the volumetric flow rate is given to you. The friction loss in flowing from A to B is 0.45 feet for flowing fluid. For a pressure head at B of 24 inches, which is given to you, what will be the pressure head at PA, right? So that's the question. Again, this is a common flow measurement device, and the question can also be asked in another way, in which you have pressure taps PA and PB, and once you know PA and PB, you can also calculate what the flow rate is, or basically you'll know the velocity through which the fluid is flowing inside the pipe, and you can use such devices to measure the velocity with which the fluid is flowing inside the pipe. Okay, so let's solve this problem. Again, the unknown is PA, and the question is what is the pressure head at A, right? So first step, always mass balance. So fluid comes in, fluid leaves. You assume steady state. If it is steady state, the rate at which mass comes in is the rate at which mass leaves, or MA dot is MB dot, or basically VA times AA plus VB times AB is 3 foot cube per second. So basically using the mass balance, you can calculate what VA and what VB are, right? That's what the mass balance tells you. Now let's go on to the energy balance. Again, just solve it systematically, right? Step by step. But obviously, before writing the energy balance, the first thing is to just to look at the assumptions, which is nothing but steady state, right? No accumulation of energy. Q dot is 0, Ws dot is 0. Now let's look at the energy balance. When rho VdA is your mass flow rate, you get the flow work from the right hand side. You have E plus P over rho, and of course, if you simplify this for this particular problem, you have obviously it boils down to MA dot times kinetic energy per unit mass, internal energy per unit mass, that's the P over rho, potential energy per unit mass, and whatever comes in has to go out, and hence you get this following expression, right? From mass balance, MA dot is same as MB dot, you can cancel it out, and then obviously ZA is the same as ZB, so that goes. There's no change in internal energy. There is frictional loss in this particular problem. So you can rearrange, and this is what you get when you rearrange: VB squared minus VA squared over 2, alpha PB minus PA over rho plus UB minus UA 0, right? So this is what energy balance boils down to. Again, the frictional loss is given to you. Look at the units, right? Be careful. We talked about this in class. The frictional loss is given in terms of feet. So what is given to you is UB minus UA over G, right? Which is 0.45 feet. Again, watch out for units. Make sure that your variables are all in one set of units, right? This is extremely important. So let's look at the energy balance again. So basically, this quantity, VB, VA, and basically what is given to you is HB is also given to you, and the only unknown here is HA, right? Which is what you're asked to calculate. Again, students ask this in class, right? When you look at the energy balance and you want to evaluate it term by term, the first question that comes to you is what is the value of the density rho? But you can get rid of the density rho because PB is nothing but rho G times HB, PA is nothing but rho G times HA. So the rho's they cancel out, right? So the only unknown here in this equation is HA, You have VB from the mass balance, you have VA from the mass balance, HB is given to you, UB minus UA over G is given to you, right? Very simple. So now you can use your calculator, plug in numbers, which is what is shown here. We did it in class, and you get a HA of 2.68 meters, right? That's it. Very simple problem. So do the mass balance, do the energy balance, can calculate what the numbers are going to be. Okay, so let's keep going on. We did this problem as well, but I just want to give you a brief, I just want to point out one important thing. So for this nozzle problem, which you can solve, which we did in class, fluid comes in, fluid leaves, and the interesting thing about this problem, which a lot of students make a mistake on, is there is one inlet and two outlets, right? So be careful, watch out, right? A lot of students are used to writing the Bernoulli's balance and all that from MEB2 as G delta Z plus delta V squared over 2 is equal to 0. So basically this does not hold for this problem because there is one inlet and two outlets, right? So watch out, just don't blindly start using this equation for this particular problem. Well, don't blindly start using any equation for any problem until you clearly understand how to use it, right? So again, first step, do the mass balance. Net rate at which mass leaves is 0. So mass comes in at 1 and leaves at 2 and 3, or basically what it boils down to is m1 dot is m2 dot plus m3 dot, right? So that's your mass balance. And same thing for the energy balance as well. The net rate at which this quantity leaves is 0. So it comes in at 1. So that's why you have minus m1 dot, and it leaves at 2 and leaves at 3. So that's why you have these two terms. And as you can see, you make some assumptions. Everything is in plane, so you neglect the Z's. There's no change in potential energy. The fluid is frictionless, so you have all these are the same. And if you look at the quantities, all you're asked to evaluate is the unknown, which is P1, because from the mass balance, V1, V2, and V3 are given to you. P2 and P3 are atmospheric. So the only unknown here is P1, right? And that's all. So it's a simple energy balance problem, and then you can go on and you can just calculate what the unknown quantity is. After that, we also did a problem from the book, 6.33. I think you should work this out on your own as well. And all this does is to cleverly apply energy balance between different sections. And by applying energy balance across different sections, you can evaluate what the unknown quantities are. So please work this out. So think, there's no just one way to do this. So do the energy balance between different points. Write down in terms of variables. See if you can evaluate all different quantities, right? So whenever you do the energy balance, make sure, right? Say shown here is a classic energy balance between 1 and 2. This is the Bernoulli's. Make sure, right? Now obviously you have one equation, which is the energy balance. So when you have one equation, then in that particular equation, there should be just one unknown. So if one equation has two unknowns, obviously you will not be able to solve it, which means you should think about doing an energy balance between two different sections, right? Where there is only one unknown. So think about it, solve this problem. It's very straightforward, but it's a very good exercise in energy balance. Okay, so these were the problems that we worked out in class, right? So now let me walk you through a couple of problems that have been posted online. I hope you do work through the homework 3, which is a bunch of problems. I thought I'll help you out and walk you through a couple of problems. These solutions have also been posted online. So here is a classic mechanical energy balance problem when you pump fluids, and the goal is to is to calculate, things like the frictional loss or how much energy the pump has input into the fluid and so on. Classic pump problems. And using such energy balances, later on we will see how we can design pumps, which is going to be pretty important, obviously, when you go to engineering design, right? Okay, so soybean oil is being pumped through a uniform diameter pipe at a steady mass flow rate. The pump supplies 209.2 joules per kg mass of fluid flowing. The entrance pressure in the inlet pipe to the pump is 103.4 kilonewtons per meter square. The exit section of the pipe downstream from the pump is 3.35 meters above the entrance, and the exit pressure is 172.4 kilonewtons per meter square. Exit and entrance pipes are the same diameter. The fluid is in turbulent flow. Calculate the frictional loss in the system, right? So the question is, what is the frictional loss in the system? That's a problem statement. Obviously, the schematic was not given to you. So the first step, read the problem statement very carefully. Try to come up with a neat schematic. Label the quantities. Put the units down. Right? This is very important. Please do not skip the step. So here is a simple schematic. Nothing complicated. You have a pump. You have the fluid coming in. And then you have a fluid going out, and the quantities are labeled. So at section 1 you have the pressure that is given to you, the velocity is V1, the pump inputs work into the fluid. Again, be careful, look at the units, right? Be very careful. So look at the units. The pump inputs work into the fluid, and that is given as 209.2 joules per kg mass of flowing fluid. Usually Ws dot has units of joules per second or watts. So what is given to you is joules per kg, right? So what is given to you is actually Ws dot over m dot. So watch out, you should have realized this. And again, the exit is 3.35 meters above. The pressure is also given to you, P2. So clearly label these quantities. That's why I say label these quantities and write down the units. This is very important. So now you have done that. First step, again, the mass balance. Do not skip this step. The pipes are the same, so basically you can assume steady state. So whatever mass comes in leaves. Since the pipe is the same pipe, obviously V1 has to be equal to V2, right? So from the appendix, I give the value to you. The density of the soybean oil is 919 kg per meter cube. So again, let's do the the energy balance now. And obviously V1 equal to V2 means M1 dot is equal to M2 dot is equal to M dot. So what does energy balance say? The net rate at which energy leaves is minus Ws dot. And again, minus Ws dot, right? And Ws dot is minus over M dot is minus 209.2. The negative sign because work is input into the fluid. The surroundings does work on the system, and hence the sign of Ws dot is minus, right? Again, this is the integral form simplified. The integral form simplified just states that the net rate at which this quantity leaves is 0. If you simplify that, this is what you get. And again, let's look at this term. Look at this term by term, right? So once you've done the energy balance, the goal is to calculate the unknown quantity. So the question is, what is the unknown quantity? So if you look at this, P2 is given to you, P1 is given to you. It's the same pipe, so all this term goes to 0. Y2 minus Y1, it's 3.35 meters. And hence the only unknown here is U2 minus U1. That is it. The work that is input into the fluid by the pump. So all you have to do is just plug in the quantities. This is P2, this is P1, this is Y2 minus Y1. This is the energy input into the fluid by the pump. Calculate U2 minus U1, unknown quantity. That's it. Very simple, right? 101.25 joules per kg. Again, watch out for the units. Frictional loss can be asked in different units. That's fine. When no unit is specified, you can write it in whatever unit you want. And the answer here is in joules per kg. Again, I want to emphasize the steps. Read the problem, clearly draw the schematic, label the quantities, write the units next to the quantities. That's very important because units can mess you up. Then once you do that, do the mass balance and do the energy balance and evaluate it term by term, calculate the unknown quantity, right? Okay, so here is another problem. This is actually a very interesting problem. Read through the problem. Again, this problem is interesting because it gives you the variables in a bunch of, I would say different units. Foot, pound force, pound mass, things like that. So you just have to be careful. And again, this problem is a very good illustration of how to apply the energy balance. So read through the problem. So basically, the problem says, okay, hold on. The pump pumps 0.2 foot cube per second of brine solution having density of 1.15 gram per cc from an open feed tank, right? Large cross-sectional area. The suction line has an inside diameter of 3.548 inches. The discharge line, the discharge line has a different diameter than the inlet line. It has a diameter of 2.067 inches. The discharge flow goes to an open tank, and the open end of this line is 75 foot. Wow, okay. Above the liquid level in the feed tank, right? If the frictional losses in the piping system from going from 1 to 2 is 18 foot-pound force per pound mass, what pressure must the pump develop? And what is the horsepower of the pump if the efficiency is 70%? The flow is turbulent, right? Okay, so that's the problem statement. Again, draw the clear schematic. The goal is to pump the fluid from tank 1 to tank 2, which is, classic engineering. Both the tanks are open to the atmosphere. In flowing the fluid from 1 to 2, there's frictional loss, and that is also given to you in U2 minus U1. And again, the different values of the variables are also given to you. And the pump is so obviously the question is there are a couple of different questions. What pressure must the pump develop, and what is the horsepower of the pump, right? So two different questions. So again, draw the schematic, label all quantities, and think about what needs to be done. So obviously, right? So again, you got to be clever at how to do the energy balance, right? The horsepower. So let's do this, right? Let's say you want to. Be careful. The first question is what pressure must the pump develop, and what is the first question. So how do you calculate what pressure must the pump develop, right? Now let's say I can do an energy balance across the pump, right? Say this is say 3 and this is 4. Now if I do an energy balance across the pump and try to calculate the pressure that the pump must develop, P4 minus P3 or whatever, can you do that? I would say the answer is no, because do you know what velocity the flow of the fluid is that is flowing through the pipe? The answer is no. And as well as, do you know how much energy the pump inputs into the fluid? The answer again is no, right? So you have to be careful. Maybe the smart thing to do in this problem is to calculate the horsepower of the pump, right? How do I do that? So basically, I think the key thing here to recognize is to first do an energy balance between sections 1 and 2, right? These are two large tanks, both are open to the atmosphere. So you can do an energy balance between sections, say 1 and 2, and then try to solve for how much power the pump inputs into the fluid. Let's look at this. Okay, so now, those are just some comments that I had. Let's go in and solve the problem. And as you can see, I'm not comfortable working in feet, pound force, pound mass. So the first thing that I did is to convert everything into SI units. These are some conversions that you have to get familiar with, maybe, as you go along. So convert everything to SI units, and I've shown So foot-pound force per pound mass has the same units as joules per kg. This is a good conversion exercise. See how to do this, and by knowing the conversions between foot, pound force, and pound mass to the respective SI unit, see how you can make this work. So I'll leave this up to you. So okay, so basically the first step is to convert all to SI units. Now let's do an energy balance, and obviously, okay, so these are two large tanks with huge cross-sectional areas. So you, to a good approximation, V1 and V2 are nearly zero at any instant in time. So both the tanks are open to atmosphere. So P1 equal to P2 is P atmospheres. So if I do an energy balance between sections 1 and 2, what it comes down to is the net rate at which energy leaves, or this quantity leaves, is 0. So so this is what you get. Basically, you strike off P1 and P2, it's open to atmospheres. You neglect V1 and V2, almost the same. They are large tanks. So basically what you have is was given by this particular equation. And again, if you look at this particular equation, U2 minus U1, the frictional loss is given to you. And Y2 minus Y1 is also known, that is 75 feet. So only unknown is Ws dot. So basically, this is the smartest thing to do, right? Because you did an energy balance between 1 and 2. Now you know how much energy is input into the fluid by the pump, or minus Ws dot. Again, be careful when you use the energy balance, and when you calculate minus Ws dot, you should get a negative number, which means that it is a pump, right? So watch out. And you can convert joules per second or watts to horsepower, and you can look up the conversion for that. And again, the pump is only 70% efficient. So basically, suppose this is the losses that occur in the pump, because suppose you input an electrical energy and only 70% of that goes into the fluid, right? So this is the horsepower of the pump. Okay, so now for the second half. So what pressure head must the pump develop, right? So this is just the schematic across the pump, right? So there is an inlet pipe, which is 3.548 inches. This is the exit pipe, which is 2.067 inches. So this is 1 and 2. This is just across the pump. So if you try to do this, in the beginning, again, right, you want to calculate P2 minus P1. There are a number of unknown quantities, because say if you look at the energy balance for just across the pump, say you call this section 1 and section 2 now, right? So you have M2 dot times V2 squared by 2 plus P2 by rho minus M1 dot times V1 squared by 2 plus P1 by rho is equal to minus Ws dot, right? So if you look at this, if you had tried to do this in the beginning without solving for the Ws dot, as you can see, you don't know P2, you don't know P1, and you don't know Ws dot, right? So too many unknown variables. If you want to calculate what P2 minus P1 is, you need to know what this quantity, W minus Ws dot, is, right? So, but from the first part of the energy balance, from between the two open tanks, you've calculated what this quantity is. So all you have to do is calculate what P2 minus P1 is. The flow rate is given to you, so you can calculate the velocities V1 and you can calculate the velocities V2. And again, this is the same energy balance, which is given to you, which is what we've done there. Obviously M1 dot equal to M2 dot equal to M dot, because there's only one inlet and one outlet, steady state. Just across the pump for the flowing fluid, I think for this particular case, you can neglect U2 minus U1. You can assume for the fluid flow through the pump, the frictional loss is negligible. So U2 minus U1 is 0. And obviously, you're just talking just across the pump, so you can neglect the rise in elevation, y2 minus y1, that also goes to 0. So as you can see from part 1, you've calculated how much energy the pump inputs into the fluid. So you know minus Ws dot, and the only unknown quantity is P2 minus P1, which you can calculate. Right? That was this problem again. The steps, just to reinforce a point, the steps to solve problems are very similar. Read the problem, draw the schematic, label the quantities very clearly, put the units down, write the energy balance, and evaluate it term by term to see and to calculate what the unknown quantity is, right? So that is it. I mean, straightforward, but just be systematic. Read the problem carefully.